Hello. I'm just making sure that my video is working on my iPad here. And I'm going to start with the questions. Oh, seems to be working, if you ask me. Okay. Etnar and Peter start calling me. Okay. All right, let's take a look at the questions and we'll go from there. Okay, now you can see my screen. We don't have very many questions, so I think we'll just start from the top and work our way down. When doing Le Chatelier's principle, how do we know if the stress is being put into reactants or products? It's not reactants or products, it's both at the same time. So if you think about something that's in equilibrium, they're happening in the same container. Everything is happening in one bucket. Let me see if I can kind of draw out something for you here. So let's say you've got a bucket here. And let's say the reaction is looking at something like N2O5 goes to make nitrogen and oxygen. Oop, N2O2. I'll bounce the equation. And this is a 2, and this is a 5, and this is a 2. Okay, so that means that inside the bucket, this is an equilibrium, which means it has some N2O5s, some N2s, and some O2s. So we've got to have a couple N2O5s. And we've got some N2s, and we've got some O2s. I'm not really doing good on numbers here, but you kind of get the gist. So what's happening is everything is in a bucket together. So when you apply stress to it, you're applying stress to everything. You're not just applying stress to reactants or products, you're applying stress to everything. So one stress that we could do for this one is to make the container smaller. So let's say we chop it down. So all of the stuff, this is a stopper thing, is pushed down into here. So my two O2s are on top and my N2O5 that's on bottom is now being stuffed down into a smaller volume. Well, suddenly if I have a smaller volume, decrease in volume, I now have increased the pressure. If I have an increase in pressure, it's got to do something about it because that's a stress on the system. So we've got to shift the reaction. So on this side here, they're all gases. So I happen to have 7 gases. Those are G's, by the way. On the left side, I happen to have 2 gases. So in order to relieve the stress, if I have a smaller volume, I have less space for all things to be. So it's going to have to shift to the left and make more reactants because that's where there's less stress. That's where everything's kind of combined, and you only have 2 instead of 7 gases. It's kind of like 2 people in a room versus 7 people in a room. 2 people in a room that's smaller is going to be a lot more comfortable for everyone. So I hope that that answers that question. You know, I can't tell you which one is being added because it's going to be on the whole system in general, and you have to decide what side is it really being added to. What time we started this? Maybe 8:53? Oh, starts good. Could you explain the meaning of enthalpy in terms of changing heat? Okay. Enthalpy is what H is, and H is called enthalpy. Now, it's technically not the same thing as Q, but in this class, it's the exact same thing as Q, which is what we all know as heat. So H, Q, and heat are all the same thing. So when you see enthalpy, you can think of Q, which is heat. Technically, it's not the same thing because if you change pressure, then enthalpy isn't the same thing as heat, but we're never going to change pressure. So that's why I can confirm and say H is Q and Q is heat, so they are all the same as each other. By the way, if you have a question at all times during any of this, you'll have to write it in red on this form and then I'll really see it. Okay, let's go to acid base. For number 8, it says it all equal. Let me look at, I'm guessing it's number 8 on the review worksheet. Okay, how do you, it says that they are all weak acids, yet the second one is Kb. How do we know when to use Ka or Kb? Oh yeah, the directions are a little unclear. That says write the Ka or Kb for the following weak acids. It because NH3 is a base. So Ka is when you're going to write the KeQ for any acid, and Kb is when you're going to write anything for a base. So they're the exact same thing, except for one's when you're writing it when it's acting as an acid, which means it loses a hydrogen. The other one is when it's acting as a base, which is meaning it's gaining a hydrogen. Okay. 56. Next one. How do you know when to use all of these different equations? All right. I can show you my square of awesome, and maybe that will help you. I know that Han just kind of gave you all the equations, but on the final, you're going to be given the square of awesomeness. Where do I have that? Without, I'm going to have to go to not screen sharing. I have to go to not screen sharing. Otherwise, I'm going to show you where my final is, and that's not quite what I want to do. So I'll be right back to screen sharing once I bypass the final and get to the square of awesome. Okay. Now we'll go back to screen sharing. Okay. Here we go. So here is the square of awesomeness. We'll kind of zoom in here. Oh, I wish I could. Can I copy and paste this? Maybe. Paste. All right, well, okay. We'll just have to go with what we got. So you have to look at my pointer. Okay, so how do you know which equation to use? Let's say that you happen to have the pH of something and you want to find the pOH. Notice how the arrow goes from left to right. I have pH and arrow points to what I want to find. That's when I'm going to want to use this equation. So then I'll put in for my pH. Let's say my pH is 2. I know that 2 plus pOH equals 14, so my pOH must be 12. Or let's say you have pH, this top left corner, and you want to find H+. Notice the arrow pushes down this way. That's when I want to use this equation, because H+ is equal to the 10 to the negative pH. So it tells me how to find that. Or let's say I have in this bottom left corner, I have H+, and I want to find pH. Notice I started here because I have H+, and I want to find pH. I go to the top. That's when I want to use this equation. pH equals negative log of H+. So in that way, I use the square of awesomeness because you start with what you got, and you go with the arrow with what you want to get, and that tells you the equation to use. Now notice down at the bottom here, you have H+, and you want to find OH-, you use this equation. Or if you go backwards, if you have OH- and you want to find H+, then you still use this equation. There's no other equation we can kind of use for that. So one last part, if we have H+ and I want to find pOH, notice there's not a direct line there. You've got to go up and over or over and up. One way to get to it that you can find. Okay, can we go over an example of buffer problem? Yes, I did do that in the upper part here. They asked for that in number 13 here. So you'll find that at about 9:51 in the other video. I wish I had my proper timer. I know that the other video started at a time of about 9:18, so you'll kind of have to estimate to get to 9:51, do the math and figure out how many minutes in are you really looking to. Okay, we're on to the other part. How does universal indicator determine the pH of a reaction? This is something that I wouldn't expect you to really know. Universal indicator and indicators in general. Let me stop screen sharing. So indicators are kind of tricky. They're a molecular kind of compound. If the indicators happen to be like, they work by equilibrium. So sometimes an indicator can be in this shape, and then it's a red color. And then when it's attached to a hydrogen or something like that, and it has a different shape, then it's a yellow color. And then when it's a different shape, it's a green color. So the shapes of the universal indicator go from this to this to this to whatever shape is based on how many hydrogens attached to it. But that's way more complex than I would ever expect you to write per se in any kind of essay like the theory that you have to write about. So if you're asking about the theory for tomorrow, you'll want to write about why is this specific compound going to be a purple color? Why is this specific compound going to be a green color? Something like that. So that's, you want to kind of say, well, an indicator tells us this, tells us the pH. pH is defined as this, which means that if you have more of a red color, it's more H pluses because the pH is lower. If you have more of a purple color, it's more the base, and bases are these sort of things, and blah, 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 blah. And you probably want to go into a compound and talk about this specific compound happens to be a blue color because of yada, yada. I think that hopefully helps you out. Why does precipitate form? I'm not going to answer this question. That is something that you should know, and it looks like that you'll have to look that up or something, or go back to your, try to put some things together about double replacement reactions. You want to talk about what a precipitate really means, maybe. Thinking about, you know, when something's soluble or insoluble, that goes back to equilibrium idea, that goes back to calculations that we made, things called KSP. Have you put that together? On the next one, can you explain hydrolysis? Sure. Here we go. Am I screen sharing? You know? Nope. I will though. There you go. Okay, so salt hydrolysis. Let's say we've got my screen here. A compound like NaSO4. Na2SO4. Sodium sulfate. So if you put sodium sulfate into water, it does dissolve. All sodiums will actually dissolve. So it splits up into its two ions, its cation and its anion. Na is a Na1+, sulfate is a SO4 2-. So this Na, if he could be attracted to any part of water, water being H2O or HOH, H is a +1, OH is a -1. If I was Na, I'd want to hook up with the minus guy, OH, and make NaOH. So now I ask myself, is that a strong or a weak base? Well, that's a strong base. The definition of strong acids and strong bases is that they actually don't stay together. NaOH is a strong base, which means it really never actually hooks up and stays together. NaOH will drastically separate right away. So will Na actually react with water? No, it won't. It won't hydrolyze water. Hydrolyze means break it apart water. It won't do that at all. But if we look at the other side, sulfate, SO4, if I was SO4 and I could be attracted to an H or an OH, I'm going to be attracted to an H. And I'm going to make HSO4, 1-. And so I ask myself, is this a strong or a weak acid? It's an acid because the H is out front. This is a weak acid. By definition, weak acids do stay together. The H does hook up to it in that way that water is hydrolyzed. It's broken apart because now my H is hooked up to the SO4 and it stays with SO4. So now what's left over is my OH-. And this right here is your base. This is what's going to change the pH. It's going to change your pH to be higher in pH because it's more basic. More basic things is a higher pH, more towards a 14. So in this way, Na2SO4 does hydrolyze water because it breaks apart water on its SO4 side and actually reacts with it to create a base. We'll try a new one other example. Okay, let's do magnesium nitrate? Sure. That sounds lovely. Okay. So I asked myself, if I was Mg2+, what would I want to hook up? An H+ or an OH-? Totally an OH to make MgOH2. But will it really do that? Well, this is another example of a strong base, so it really won't hook up. It won't hydrolyze water because MgOH2 won't stay together. It's a strong base. It'll always be an electrolyte or fully separated. NO3 on the other side, NO3 is a 1-, so he would want to hook up with H to make HNO3. And then I asked myself, was that a strong or a weak acid? That's a strong acid. So will it really want to hook up and stay together? No. HNO3 will not stay together. Strong acids and strong bases will always fully dissociate, separate the H from the NO3, which means that that won't be made. So does MgNO3 really hydrolyze or react with water? No. And since it can't react with water, it will be neutral in pH because it can't force H2O or water to separate into its H's or OH minuses. And if you don't separate into H's or OH minuses, then you really can't change the pH. Okay. Let's see here. Okay, do we have to memorize the strong acids? Yes, you do. Also, does that mean that insoluble would be hydrolyzed? Indicator wouldn't work because it did not change what was tested. You'll have to ask yourself what insoluble means. Soluble versus insoluble, does that mean that nothing dissolves at all? Does that mean that some dissolves? Does that mean hardly nothing dissolves? Does that mean a lot dissolves? You'll have to ask yourself, when something says it's insoluble, does that mean it completely does nothing? So sorry to that person, I'm not fully answering the question, but I'm hoping I'm guiding you to some place that would help. Could you explain any outliers and strong bases? An outlier, the strong bases that I would expect you to know is everything in the first and second column. I'll put my time here. So a strong base will be anything from the first and the second column. The only thing that's not a strong base would be in the second column, there's beryllium. Beryllium oxide, hydroxide is not a strong base. Why is calcium? Calcium hydroxide would be called a strong base. As to why there would be exceptions, just because it doesn't have a high enough Kb. Kb tells us how dissociated something is, and so if it doesn't have a high enough Kb, then it means it doesn't fully dissociate enough. Calcium hydroxide would be a strong base. I'm kind of waiting to see if this person has something more to say in the. My anonymous duck is what you're labeled as, my friend. So the only outliers of strong bases is beryllium hydroxide when you're dealing with column 1 and 2, which are the only strong bases. Unless Han told you something different, but I don't think so. Okay, I'll wait for you. I'm going to see what Edna had to say to me. We're on like a 2-minute delay. Is it a hard test? Nobody cried. I asked one person after, I said, was it a shocking test? And they said no. I said, good, I hope to go for fair. I think they thought it was a fair test. People weren't scrambling at the end. That was good. Were they crying on the inside? I don't think so. I mean, you basically know half the test. Half the test is your flow chart and the theory and claim, and you know how to write that. If you don't know how to write a theory and claim, you should go back and look at your rubrics for that. What equations are you giving? I am giving, this is posted on my website. Oh, you can't see this. Hey, let me share the screen with you. This is posted on my website, but this is the sheet that I'm giving you, plus Han's equation, because this one, these middle ones here are the way I would have taught titration neutralization equations, and Han taught it differently. So I'm going to write Han's equation on the board. You will find my equation on my website. It'll be, if you click on this honors chem part, right down in here, final exam equation sheet. Boop. So there I put in Han's equation. I scanned her in. Is it split 45 minutes for that? No. I mean, you can spend any amount of time on anything that you want, really. I figure, I timed myself when I did the final. I don't. If I have that copy still. The multiple choice took me 6 minutes. And the short answer took me 6 minutes. So if I multiply that by 4, then you're looking at 15 minutes for the actual written part. 15 minutes, I figure, is actually being in the lab, which leaves you 25 minutes for your writing about the lab part. So people weren't seeming to have, like I said, a tough time on time. So you can spend time wherever you want to. There's no rules on when you can and cannot be in the lab. Okay. Oh. I'm going to answer this number 9 question. What's the difference between yours and Ms. Hahn's formula? I think I'm still screen sharing. Let me check. Yes, I am. Okay. So let's go back here. If you click on the equation sheet, here's Hahn's. She's got all the A's on the left and all the B's on the right. And when you do it, then your A on the left, the big A, is the number of hydrogens. Like if you have H2SO4, it has 2 hydrogens, right 2. If you have HCl, it has 1 hydrogen, right 1. And the B is how many OHs you have. Like NaOH would have 1 OH. MgOH2 has 2 OHs, so the B would be 2. My equation is this top one here, and you can see I have A's and B's on the left and B's and A's on the right. And that's when I have a balanced equation and I do coefficients. So that's when my big B stands for the coefficient from the base and my big A stands for the coefficient from the acid. If you want to see me do one of those, equation in the first video, I do it right here at 9:50 is when I ended it. So somewhere between 9:45 and 9:50 is when I actually did my way and Hahn's way. And then that way you can pick which way you want to go. Did they cry on the inside? That's hilarious. What is being excluded again? Is it only the topics on the review sheet? Yes, only the topics on the review sheet are going to be on the actual final. Hey, no problem. You won't cry. You'll do great. I'll wait for other questions. I'm going to listen to Etnar's voicemail to me. Maybe the lab burned down or something. Etnar and Peterson calling me? This could be a problem. All right, folks. You're going to do great. I'm out. Good luck. See you tomorrow morning, bright and early.